Okay, welcome to MGM. So we are into generative modeling now, and today we will study generative adversarial network. Today it will be the theory part, how this method was theoretically using maths, how it was derived, and then in the next lecture we will look into the practical implementation details and algorithm. Today I won't write the algorithm, but I will just connect the dots, various ideas, and how it led to this method. Okay, so let us do generative adversarial networks, which is one of the key methods for generative modeling these days. Okay, as the name suggests, it's a generative model, but it has some adversary. Okay, and from maths point of view, it will be a min-max problem. Okay, so there will be an adversary that tries to maximize, and there will be another agent that tries to minimize. So those type of problems fall into min-max problems. Okay, so we will get to know about these details. So let us recall what does it mean by generative modeling, right? So given a set of samples, okay, so we have to recall. So in generative modeling, what we want to do is, given set of samples, let us say xn, that follows underlying distribution given by p, right? So xis can be text data, okay, words of the text data, or it could be images. Okay, so whatever problem you want to model on, that you want to generate, first you will have some samples, and you don't know obviously p, because that's exactly your target, right? To know which is the distribution from where I can generate more, right? So one possibility is that we can do a density estimation. So given these samples, I can construct an approximation of p based on this. So it's like a density fitting problem, right? Just like we have set of points, we would like to fit a line, okay, and that line will is an approximation for us, right? And optimize for that theta in the template, and maybe have an approximation, right? So we can construct a density estimate so today's class may extend a little bit by more than a half, by half an hour. Okay, so I may go for 2 hours today. Okay, I want to cover the theory part in one shot. Okay, it may or may not. Okay, I'm just thinking. Okay, so what we can do is, we given set of samples, okay, underlying distribution is p, we don't know, and so one possibility is that based on the data, I may want to fit a template distribution. Okay, this template is this parameterized by theta. So let's say you have Bernoulli, right? And you may have, so p theta to the x 1 minus theta to the 1 minus x. Okay, so that's one template distribution you have, or you can have a normal distribution. Okay, so 1 by square root of 2 pi e to the minus x minus mu. So there mu is your parameter, which is, you can think, so in normal you have two parameters, theta 1 and theta 2. So that's another template distribution that might fit in this data. It could be Bernoulli distribution that might fit with the parameter theta. It could be exponential distribution. It could be any distribution. Okay, so those are inductive bias that I will choose in advance, and I will feel that, okay, that's a good one. Okay, but that's something we'll look into the data and decide what is the template. But once we have that, we find a theta. So basically we will maximize this this over theta, because it's a probability, so we will maximize this for all the x1, x2, xn. What is the theta for which this is maximized? This is maximum likelihood estimation that we do, right? So in the last class, we have done maximum likelihood estimation, and that's how we can fit a distribution. So one possibility is to learn an approximation of the distribution that I want to know via some template distribution, and once I have that, I may want to sample from here. So we can then sample from y p hat theta x to generate. Okay, that's one possibility. And in this case, as we have seen in the last class, we roll a die and then we form a histogram. Histogram is nothing but the PDF or PMF. So based on the data that I have now here, what I'm trying to do is fit a PDF. So, okay, so this is my x1, x2, and learning a p theta is like learning the fitting the distribution, which is in this case a PDF, and we knew what are the next steps to sample. It's not just the PDF. There is a second step is when I convert this to CDF. Okay, and this is our PDF. Okay, and the trick that we used is that we look into CDF, and then this gives me ranges between 0 and 1. So this is uniform 0, 1, and from here we go, and then we start generating a data. Okay. So sampling, even after half the PDF, it requires one more step, because I know how to sample from the uniform. From uniform, I look into the CDF of this PDF, and from there, I start sampling. So there is an inverse CDF involved. Okay. Okay. So this is one template that actually we know from the last class, that this is one way to do things. Okay. What GAN does is GAN does a approach where it uses some similarity measures between two distributions. Okay, and we will see that they are kind of related. Okay, so like having likelihood estimation or doing a similarity measure are related things. So what is done in GAN is you go for certain measures, okay, where I want to learn this distribution, and this is the underlying distribution, then I want to know how far they are. Okay, so it's kind of a top-down approach. Let us say I have a P, and my approximation is P theta, and what are the good ways to measure the distance between them? And with this measure, I will derive an algorithm to find a good P theta itself. Okay, so that's why I call it a top-down approach, but they are related. Okay, so hence in this line of research, you look into ideas where you look into measurements between two distributions. Okay, so that's why from here I will start with these ideas of how we measure two probability distributions. Okay, so how do we measure two distributions? Okay, at the end of the day, you want this to be close to this. Okay, so we want to know what is a good way to measure. Okay, even if I have generated an approximate PDF, I still want to know, is this quality-wise good approximation or not, right? So how do we measure two distributions? So this is something statistics people have been doing for a long time. They have many types of measure, okay? So if we look into the early work where they discuss a lot about measure, so one of the paper by Adhikari and Joshi in 1956, they have a paper, it's called Measures of Distance. Okay, these things can be picked up as a project. Okay, so I will list these papers as a project. So these are the guys who were initially documenting these different type of measures. And there is one by Rao, 1952, and here in his paper, Measures of Separation. Okay, so these are a bit synonymous, but with sometimes with different applications. Okay, so they may be doing probability distribution comparison in signal processing or in some other area like information theory and so on. Okay, so but all were essentially trying to measure a pair of distribution. Okay, and then so this Rao is very likely the same Rao because it's the most famous guy in statistics from India. So C.R. Rao, and this is the road that on which beside our institute. Okay, C.R. Rao. So if you see the institute address, we have C.R. Rao Road. Okay, IIIT. Okay, so so he also got associated with I mean he was mostly working with Fisher and so on. So he has numerous books on statistics, many results in his name. Pick any book and you will see filled with his name. Okay, okay. So and Fisher was one of the very famous statistician. He was his supervisor, Rao's supervisor, and all these guys were instrumental in creating modern theory of statistics. And then we have papers by Chernoff, 1952, and Kullback. So this guy will be interesting for us. Okay, Kullback, 1959. So measures of discriminatory information. Measures of discriminatory information. And we have Kolmogorov, 1963, measures of variation distance. The reason why it's good to look into this paper even as a research student is some of the ideas you will write a paper on will come from some variation of these measures. GAN is just picking one of the divergence measures, which is Kullback, and building on this, and then many papers were created out of that. But as a researcher, you would like to know more, and that's my goal in this lecture, is to show all the intricate details that you will not find in general elsewhere. Okay, not even compiled as in one place. Okay, these are tied together for you from papers. Okay, so let us see. It will be a very interesting lecture today. Now, okay, so obviously these measures are, as I said, depending on the problem at hand, they found that different measures are useful. And for image generation task, as I said, Kullback divergence seems to be a good one. So we will do that a lot today. So a common property in these measures is that they measure, okay, basically, right? So if I want to compare, it's just like the norms we have in hand, right? But those norms are for vectors, right? And we use norms in a way that we want, right? So sometimes I use 2 norm because I know that it's differentiable, 2 norm of a vector, right? So, and then if I have to compute the difference, then I do x minus y, okay, and if I also square it, and then this is a measure between 2 vectors x and y, and the choice of 2 norm and squaring it is because I need some kind of differentiability. But then there are cases where I will do a 1 norm, and in this case my interest is to preserve sparsity. So you see, I can measure 2 different things, but then I may measure them with a choice that I have in mind. They will do the closeness, but they will do the closeness with few additional properties in mind, okay? So if I use 1 norm, then it does preserve sparsities. If x and y were sparse, and I want an approximation y which is close to x but keeps sparsity, then 1 norm is preferred. So depending on the problem at hand, if it's a problem that involves sparse variables, then you go for that. And then there are problems where differentiability is something I need because at some point I feel useful to use gradient descent to minimize the loss. And then I need some differentiability, okay? And there are many norms. There are function norms, right? F minus g, okay? How do I compare 2 functions are close to each other or not? Then I will take an integral and check that whether the area under them, okay? So area under the f and area under the g are kind of close to each other, right? So that's when I will say that this is area under f and this is area under g. So here I need a norm, and then here also I can make it let us say L2 norm, that's capital L2 norm between fg, okay, and so on, okay. So we are familiar with quite a few of norms that we use in the vector space, but we are not that familiar with the norms that is used to compare 2 different distributions, okay. So in general, when we are looking at the norm, then what we expect is that when they are close, the distance should be kind of 0, okay. So those could be a guiding principle of these norm as well, and if they go apart, then the norm should also increase, okay. So these are the few things that is usually expected from a norm. So one of the ways in statistics what people look at is ratio, or sometimes you can call it as a likelihood ratio. So rather than looking at the difference, they look at they like to look at the ratio, okay. And so if they match, then phi x will be 1, okay. Now to make this 0, like consistent to what we usually expect from a norm, if they are equal, then they are 0, right? So one possibility is that I make a log here, okay. So log of p2x by p1x. Then when p is 0, if p1 is p2. So if 2 distributions p1 and p2 are equal, then the difference or the measure is going to be 0, okay. And we can also generalize this in terms of like a relative difference. Then I will look into this as an expectation also, okay. So on expectation, right, because these are probabilities. So I will say, okay, on average, are they going to 0? Okay, that's another way to look at that, okay. Because probability distributions are like that, right? So if I can say on average, what do you think log p2 by p1 Does it go to 0? Okay. So, so then it could be a slightly more generalization where I say, okay, on average, and x follows, let us say, p1. Okay, so on average, for p1 and p2 both are defined for x. Okay, let us say. So this is one possibility. Okay, on average, I could do p2 also. Okay, where x follows p2 and so on. So these are the intuitive ways to initially introduce how people work with probability measures. Okay. Okay. So a common property that we expect is, so I will just write down what I said. Common property that we expect from measures is that it increases as two distributions move apart. And we call such property is called measure of divergence. So hence we are looking for, can we have a general method, okay, of general method of generating measures. Okay. So since they are probability distributions, just L2 norm and all these things won't make sense in this case. So one of the probability measure is by Kullback and Kullback-Leibler, okay, or Leibler. So let us start with one of them, okay. So Kullback, which is essentially this, what I said, okay. This is how they came up with this. So Kullback. So first time we write the full name, but then we will call it KL, okay. It's not the cricketer, okay. It's the Kullback-Leibler measure. So here we will specify what exactly it means, right? So as I said, I am taking an expectation, right? So expectation means, so expectation of a function, right? So expectation of a function, and this is with P1. So in the sum you will have P1 times this calculated at those x in the sum. Okay, so we just invoke what is the idea. This is why we did the probability and statistics, right? So if I have to, and x follows some p, then this was xig xi I, right? I on the range of x. So this was called lotus, right? So this is the property we invoke, right? Law of the unconscious statistician. Okay, it's a funny name, but this is how we compute expectation of a function, right? So this is how, motivated from this, Kullback defined this expectation. Okay, so this is sum of px log px by p theta x. Okay, and this is exactly what I said. So just for convenience, I will write this again. This is nothing but expectation of x follows p log of px by p theta x. It's not necessary that it has to be in the discrete form. You can remove the summation and put an integral there also. Okay, if these are continuous distributions p and p theta, then the same idea for expectation follows by removing sum by integral. Now this is an example where I want to compare form expectation of yeah, this is p of xi, sorry. Right, yeah, okay, I got it. So this is p of xi, PMF at xi and the function value at xi, right. So this is the discrete. That's why I use a summation. Okay. So summation over all the x indices that you have in the range of x of the p, right? So this is Kullback, and intuitively this measure makes sense, because if p is close to p theta, then everything is 0, and hence they will be decided to be equal. And once they diverge, then the log of them starts becoming both are positive, being a probability, p and p theta both are positive values. Okay, so their difference will increase, and then log will increase. Okay, in some sense. So basically, they will diverge away from 0. Okay. Okay. So this is the kind of measure they use in contrast to the measures that we are familiar with in terms of difference and so on. Okay, but if you go to like classification problem, they use losses that involve log and so on also. Okay, so there is a connection there. I will come back to that a bit later. Why log becomes interesting in losses, but for the moment, let us keep this as a definition of KL divergence. Now, as I said, one possibility initially from the last class was sample approximate via some likelihood estimates and so on. Somehow you estimate the density estimate, and then CDF, and then find a pushback that goes there, which involves CDF inverse. And in the GANs, we start from the top-down approach. We say, given two distributions, how do I know they are close or not? Okay, and from there, we will derive some ideas. Okay, we will derive something interesting, very deep, coming from maths. It's variational approach. Okay, variational approach usually used in integration, used in probability and statistics. Partial differential equations, where you use variational approach to solve a problem, because most problems are intractable in general. So you use some test functions. Okay, and with that test functions you can integrate. So so variational approach in general is very, very deep. Okay, someday if I have time, I will relate all these ideas in one class, because knowing this helps you to create ideas. Okay, because in some other problem you may do some other kind of variational approach that gives you another paper. Okay, so for today's class, to keep things tractable, let us go step by step. Okay, and then so if I have this measure, as I said, what do I do with it, right? Initially I said, okay, I have a template and I do something like that, but then here in this top-down approach, you will say, okay, so what, right? You said there is a measure you have to compare, but how does it give me an algorithm, right? I want to generate data and so on. I don't even know p theta in your case, right? So one thing to relate as a first step is KL is very, very similar to, in fact, it's equivalent. Minimizing the KL divergence. So once I start with a measure, then my goal is to minimize, just like in any other problem. Once I define a loss function, my goal is to minimize the loss. Okay, it could be prediction problem, whatever problem I want to approximate. Here also I am asking the same thing, right? For whatever p theta you gave me, if I am going to infimize this, then what does it lead me to, right? So let us look into this. We will do an infimum and we will see what does it tell us. Okay, so let us try to minimize KL divergence, because that's the thing that we usually do. Once we have a measure, we will minimize KL divergence. Try to minimize, right? And see what do we get. Minimize KL divergence. See, if I start minimizing KL divergence, what do I get, right? So let us say I infimize, and the parameter that I have in hand over which I infimize is the theta. Okay, so it's infimized over. So which values of theta I expect p theta to be close to p, right? So this is d, p theta, and this is, so this by definition is the sum of the, so I will copy this over here again. So this is px log px by p theta. So this I just copied the definition, and then I want to see how I can split this further. Okay, so if I have to split this, and then there is an infimum here, because this infimum over theta continues. So this is sum of px log 1 by p theta x minus px log 1 by px. This is x, this is all out of x. So I have done a splitting of using the property of the log. So I have seen this term as px log px times log of 1 by p theta x. So then multiplication becomes addition, and then px I also changed. I reversed the ps. Okay, so if I have to derive this step, then just focus on the log part, right? So log of I can write this as px plus log 1 by p theta x, and this I can write this as minus log of 1 by px, and this remains as it is, log of 1 by p theta x. Okay, this derivation is clear. Okay, so this only log splits like that, and px applies on both, so that's fine. So this is the trick we did. Okay, so then, so after doing this, we realize that there is an infimum all the time. We realize that there is nothing to do with theta on the second term, right? So infimum won't apply here, no theta here. So essentially it's okay to kind of forget that, because there is no contribution of theta from there. It's a constant. We can add it back later on after infimizing, but for the moment it has no use as far as infimum is concerned. So we can focus on infimizing only the first term, which is px log 1 by p theta x. Okay, and I can move p theta on the top, then I will get a minus out of that. So this will be infimum over theta minus px log p theta x. Now since there is a minus, if I want to make it plus, then I will change infimum to supremum. Okay, so that makes sense. So this is supremum of theta px log p theta x. And if I look into this, then this is nothing but kind of, this is expectation of p theta x log of px. So, and I am maximizing that. So it's the same as saying doing a maximum likelihood estimation of that. Okay, so I'm doing a maximum likelihood estimation of log p theta. Okay, so this is supremum of theta, and this is log of p theta x. So this is nothing but maximum likelihood estimation, MLE estimation. Okay, that's what we do in maximum likelihood estimation. Given a point, say to is a point x, we fit a, this is, you can think of this as log maximum likelihood, okay, because we have a log also. Okay, so this is like log maximum. We have done this in the MLE class, okay, maximum likelihood class. We had both variants, MLE and log, because log is increasing function. So either I maximize p theta or log of that will give me the same point. It's a monotonic increasing. So we have seen all this in the last class. So what we want to say now is minimizing the KL divergence is the same thing as having a maximum likelihood estimation over the given data. Okay, okay. So that's an interesting observation, right? And then it's an interesting observation, and then it also tells us where we are going then. If it happens that even with a top-down approach where I have a certain measure to compare, and that also boils down to maximum likelihood estimation. So what did I get out of all this? Okay. So what you get out of all this is a second key idea in this GAN work is a variational approach. Okay, that we will go into the as a next step to derive an algorithm out of this. It is equivalent. On the hindsight, we know that it is equivalent, but there are problems with this approach because there are this inverse CDF and all this is still needed after this. Okay, that's why we want something else from here. Okay, so let us look into something else. Okay, let us look into something else where inverse CDF is not needed. It gives me a direct approach. Okay, via optimization method like solving min-max problem and so on. But let us go there. So up to here, I would say nothing much interesting. But you have to trust me that right now that knowing little bit about KL divergence is important before I introduce the key idea. Okay, so let us first understand KL divergence. So one thing about KL divergence is it's a convex function in P and P theta. Okay, it's convex in P and P theta, and these are the reasons why you will see so much of convex analysis used. This is the reason why I stress on maths, because ideas get generated from there. Once idea is there, you can always implement, but how they are developed needs a lot of stuff. Okay, so the first property that we will study is that the KL divergence is convex. So I have defined convex before, so I'm not going to do that again. So convex when I was doing Jensen's inequality. Okay, so in the pair PQ, so if I have two distributions PQ and as a function of PQ, it's convex in the pair, meaning it satisfies the criteria KL lambda P1 plus 1 minus lambda P2 and lambda Q1 plus 1 minus lambda Q2 is less than equal to lambda KL P1 Q1 plus 1 minus lambda KL P2 Q2. So this is essentially what we have to prove. Okay. When we are proving convexity for a pair, this is how we prove. Okay. This is what we are supposed to prove. So where P1 Q1 and P2 Q2 are two pairs of probability distributions, and obviously 0 less than equal to lambda less than equal to 1. So the proof of this is we write KL as PQ is sum of PX log PX by QX. So the parts where these are kind of straightforward, I go faster. Okay, so we use the log sum inequality. So this is an inequality from like you may have seen somewhere while doing problem solving in high school or whatever. Okay, so this log sum inequality says is summation of AI log of AI by BI, I equal 1 to n is greater than equal to sum of AI, I equal 1 to n, and log of sum of AI by sum of BI equal 1 to n. Where AIs and BIs are non-negative. So this is an inequality that one can prove as an independent results. It's just an inequality. You can try your hands on this. So where AIs and BIs are non-negative, meaning greater than or equal to 0. So we are going to use this. Yeah. Yes. Yeah. That's right. So you will. Yeah. You can prove this using Janssen hint. Yeah. Right. This is an application of Janssen. Okay, that's a hint. Janssen's inequality will work here. Okay, and not log as such, but negative log will be convex, and then you can work with that. Okay, okay. So we will take this inequality, and our goal is to prove that KL is convex. So hence we have KL lambda P1 plus 1 minus lambda P2 is lambda Q1 plus 1 minus lambda Q2 is equal to sum of lambda P1x plus 1 minus lambda P2x, and then log of lambda P1x plus 1 minus lambda P2x divided by lambda Q1x 1 minus lambda Q2x. So basically we have just put these guys in the KL definition. Okay, so far we have not used this inequality. We have just put this in this notation, and when we look into that, it looks like, okay, log of some fraction, and then in front we have something. So, and we have sums as well. So basically the left hand side. Okay, so we look into this. So this should be without using the inequality still, we will get an upper bound of this, and the way we will do this is that we will drop one of the denominator terms, and obviously these guys are positive, this being PMF, this being PMF, and lambda is positive, so both guys are positive, so dropping one of them will always increase. So if we do that, then we have lambda P1x log of lambda P1x by lambda Q1x plus 1 minus lambda P2x log of 1 minus lambda P2x divided by 1 minus lambda Q2x. Okay, so you can see conveniently I have dropped some of the terms, and I have also done the splitting. So are you kind of convinced with this, right? See, if I have to look into the first term, what did I drop, right? I retained. It's not just the denominator I see now. It's also terms from the numerator I have dropped, right? Then we have to be a little bit. So this term is fine. This term will multiply with this, right? But then when I'm multiplying with this, I retain only this guy, and I retain only this guy in the first part, right? And when I'm looking into this guy, then I have this, yeah. So I retain this, and then I retain this. This seems to be a jump to me right now because it's not straightforward to drop like this. It may be true, but it's not very clear how. Or did we like somehow already use the log sum, or it could be that we use the log sum here, inequality here. Okay. Some of these no, we cannot use that because otherwise the sum would have split, but here I see sum to be applied throughout. Yeah, I mean, if you see this term, how it could have come, this multiplied with this, let's say. So if I multiply with this, I can certainly drop this term and I increase, but then what about this guy, right? So it's a question of, or maybe that's where we use the log sum maybe. So what we are trying to ask is this log of a plus b. Yeah, this is p2. What is common here? Okay, nothing is common here. Denominator is completely with q2. Yeah, denominator is completely with q2, right? So it's like c plus d, and this we are saying is less than equal to log of a by c. It seems to be, right? A plus b by c plus d is less than equal to a by c. That's what I did, right? So yeah, let me write it here, then we will check. So what was that? A as
A1 as lambda b1, A2 as lambda b2,
okay,
and b1 as lambda q1,
lambda
q1,
q1.
and b2 as 1 minus lambda q1.
It was b1 or p1 you were saying?
P1,
P1, right? Okay.
and A2 is 1 minus lambda. 1 minus lambda A2. And P2 is 1 minus lambda Q2.
Okay. Yeah, so let us check this. Yeah, it's, we have greater than equal to sign, right? So basically this, that is on the left hand side there, lambda p1 is like a1 and this is like a2, and then yeah, it follows actually from there itself, right? And then we have log of a1 by b1 log of this, that's from there itself directly. I was thinking there is one step and then there is this log sum, but it's the one step, this one step is the log sum itself. Okay, that's right. Okay, it follows. I mean, just put it there and it follows. Okay, okay. So this is actually log sum inequality. Okay, and then this is KL P1 Q1. This is KL 1 minus lambda P2 Q2. So this is yeah. I mean, we can do a kind of simplification here, right? So this is, let us say, lambda of P1x log. Just take the kind of remove the lambda basically. Just a simple step, but just write it clean way, and then plus 1 minus lambda KL and P2 Q2. Okay. So I mean this one's more step, P2 x log P2x by Q2x. So basically I cancel these lambdas, just write in green form, and then now it is in the KL form. Okay. So this is lambda KL P1 Q1 and plus 1 minus lambda KL P2 Q2, and this is what implies that KL is convex in P1 and P2. So we can do a simple computing KL, computing with KL divergence. So given some distributions, let us say, so this is just a quick example of showing how to compute KL divergence. So let us say your PMF values are given to you, Px, Qx, 9 by 25 or 12 by 25, or you have 4 by 25, and then this probability distribution is 1 by 3 by 3, 1 by 3. So I'm given two probability distribution Px and Qx, then PMF values will be given to you, and you are supposed to form the KL, compute the KL. So this could be like small questions in the exam, right? So then you do this Px log Px by Qx. So then you do this 9 by 25 ln 9 by 25 by 1 by 3 plus 12 by 25 ln 12 by 25 by 1 by 3 plus 4 by 25. You can do this, complete this later on, just for completeness. Like this is how we compute probability measures, KL. So one reason to do this example was KL of PQ is not the same as KL of QP. Okay, so that you do this in the QP way also. So that D, so it's not a symmetry, hence it cannot be a metric. Okay, so metric that we study PQ is not the same as DKL QP. Metric must satisfy symmetry. So if you recall a metric, so it's a function from M to R, then D is a metric or distance function when it satisfies, let us say, D of xx is 0, D of xy is greater than 0 if x not equal to y, and dxy is equal to dyx, and triangle inequality is the fourth one, dxz is less than equal to dxy plus dyz. So this is how in vector space we define a proper metric, and what we have just shown is that KL is not a KL divergence is not a metric. Having a metric would have led you to many interesting things like topology, defining right topology on this, just carry over the real analysis for KL, but unfortunately it won't happen. But many of the other things are satisfied. Okay, so this is satisfied for KL, this is satisfied for KL. This I have not verified triangle inequality, but most likely this doesn't satisfy, and this we have already shown that with a counter example. In fact, triangle also doesn't satisfy. Okay, we can, yeah, so this could be a good exercise for you. So that triangle inequality is not satisfied for KL. Okay, I mean distance is one way to impose a metric and the corresponding topology, but as I said, it may create its own topology in its own right, because we know that distance doesn't necessarily have to define a topology, right? You just need concept of open sets. But most people, what they do is they always work with, when you are doing computing, you are always doing distance measures and so on, and that's why most people do metric space only. Okay, those who don't know topology, it's fine, it is not a critical thing in this course. Okay, so right, so some of the additional exercises I have listed. So this is one, and then another exercises that I have not filled is prove the log sum inequality. Oh, that I already listed, sorry. So that's done. Okay, sorry. So I've already written it that it's exercise. Okay, so yeah, triangle inequality you prove. Okay, you find a nice example. Now let us go into let us come back to the track. We are a little bit familiar with KL divergence now, because that is the main tool for generative adversarial nets. So having a familiarity around this was needed. Now we will try to generalize KL. Okay, so we have KL. Okay, now we will generalize to some variational approach, and while doing this, we will kind of, yeah, obviously, like we will look into a yeah, for the moment, let's say we take help of convex analysis. So we need conjugates, okay, conjugate function that we study in convex analysis. That is a way to get variational approach, where I want to compute an integral, but in its own form it's not tractable. But if I start applying some test functions, then it starts becoming integral. A very generic approach, right? I'm not saying that what I'm saying is absolutely precise, because it varies from, if I'm solving PDE, the variational will be done in different way. But essentially what it means is that I'm supposed to do some integration, complicated integration. As such, it's not tractable. But if I start using some test functions along with it, and maybe maximize over such test functions, it will give me a reasonable approximation of the integral itself. A very vague way to say that these are called variational approaches. Approaches where your integrand is complicated, you apply some kind of a test function, and you kind of approximate. Of course, the original was not tractable, so your only approach is to approximate. So you kind of approximate via nice choice of test functions. Okay, a class of methods that follow this are called variational approaches. There are very vast applications of variational approaches. If you do PDE, you will form an integral like Euler-Lagrange. Okay, so given a PDE, grad square u, okay, and minus ut something, right? So it's like some advection diffusion problem or so on. I go to if a corresponding integral of this is an optimization problem. Okay, so minimize and some function here, and now in general, so this is called Euler-Lagrange. Corresponding to a PDE, there is a Euler-Lagrange, and then from here you may use some kind of a variational approach, because the integral may not be easy. The reason why it's good to know these things is that as a researcher, your ideas come from there. Ideas don't come out of blue, right? Idea comes from looking into similarities, what they did in some other area, and what was the generic idea. Oh, I need to apply some test function. Okay, so let's see what kind can I do for generative modeling. Okay, so this is why we need this. Okay, so key idea is this: not tractable, but go to something tractable. Okay, and with a confidence that what you did is a good idea. Okay, so let us now go to so the next topic is we will generalize scale divergence. Okay, to get some key ideas. By key idea I mean go to the variational approach idea. Okay, which is a practical idea. So one thing I notice in the KL divergence framework is that I have dpq is sum of px log px by qx, and if I kind of reverse the px with qx, then it seems like I can do something like this: px minus log qx by px. So that's the trick that I did. The log ratio I change, and it becomes a minus. Now from there I get the hint that there is some generic way to look into KL divergence. If I stare in this, and anyone who has done convex analysis, or someone like one of you said that Jensen's could be applied, that's because you knew convex analysis. You knew it has to do with convexity. Here also I see minus log as a convex, and then immediately I see what if I generalize to any convex function instead of minus log. So can I get some very generic way of defining divergence, right? So this we see is convex, minus log is convex. Then you may say, okay, what if I put in any other convex function in place of minus log? Okay, that might give me some interesting measure which is tractable. Not just tractable, it gives me a wide variety of measures and compare and see which one is good for certain generative task. So the key idea here is replace minus log by convex function by generic convex function. Now obviously you will you would like to know that while doing so you would like to know that the basic nature of divergence measures are satisfied. In other words, if P is equal to Q, then it should essentially go to 0. That's what was our expectation. So we put a convex function for sure, but in such a way that it maintains the fact that P being equal to Q goes to is 0. If P diverges from each other, then the value of KL is increasing, things like that. So one possible restriction obviously seems to be that convex function will be such that, okay, where when these guys are equal, it should kind of vanish. In other words, that convex function should be such that f of 1 is 1, for example. Okay, so in this case our convex function is for KL, our convex function is fx is minus log x, and obviously in our case the x was px by px, qx by px, and in this case it became minus log qx by px. Okay, so that's one. So what we want is that not just any convex, but we what if this restriction is allowed, okay, where at 1 it vanishes, and that gives me a good measure. Okay, when they are equal they must vanish. So a detailed study on this generalization was done by the name of this paper, maybe not written, yeah, the name of the paper is there. And this generalized approach, where the log of the KL was made into a generic convex function, was studied, and it was called F divergence for the fact that this minus log was replaced by some F, and they call it F divergence. Okay, where F is convex with F1 is 1. Okay, so then we go to F divergence. This was introduced by, so these papers that we encounter, we are taking some ideas from there, but as a project you can go and read in more detail. Okay, so these are listed on Moodle, okay, or going to be listed. Okay, so this is called a general class of coefficients of divergence of one distribution from other. From another. Okay, and S.T. Silve, 1965. Okay, so this is where they reading original papers is always interesting, because there you connect the dots. Okay, why they thought it like that. Books are good to only some extent. The only problem is that to study so many papers you don't have time, but the actual key ideas, you know, when someone is crafting the idea, that's when you know how it was done. Books give you a very polished idea, right? So when you go there, they will say, oh, we tried that and this was not this way and so on. So they will show the full detail. So this paper is a good to read as a project. They will be papers. You read papers. Reading paper and presenting, yes. That's the idea behind projects. You can also implement the code if you want in the paper, but a full detailed explanation of the paper as a PPT is the requirement. Yeah, so that's your choice, right? There will be paper which does not have too much maths. So that will be freedom, right? There are a list of paper, you have to do one of them. Okay, as a group also. Okay, So now we will generalize this idea. Basically, we will replace minus log, and we will do a little bit of tweaking here, p with q, but you will see that, but still equivalent, okay? Like what I said, the notations change a little bit, but so definition of f divergence. So we can discuss about the projects in detail later on. Let us go with the class. So let f from R to R convex lower semi-continuous function such that f of 1 is 0, okay, as we wanted. We define f divergence between two distributions with densities p and q on x by df p q. So we use the integral form of the expectation. Just replace this by integral. Okay, so sometimes we use discrete notation, sometimes we use integral notations, I mean similar. Okay, qx f of px by qx dx. If you compare with the GAN, the p and q seems to be flipped. Okay, but that's fine. Everything fits there. We will take certain f which will produce the KL divergence. This is called f divergence because we introduced an f. Okay, we introduced an f. That's why it's KL divergence. Now, KL divergence is a special case of f divergence. So the fact that in KL in f divergence they have the little bit of switching of p and q is not exactly the minus log f that I told you. The way to do is like x log x. So then if you have p by q, the p remains and q gets cancelled, because the way they have written in the KL is p should remain. The way f divergence is defined is that q remains. So the trick is to now take x log x. Okay. So and then this negative is also absorbed because this will be p by q. Okay. So let us do that and you will see. So they could have done this also, but maybe there was a reason not to do so. So they did a little bit of change, but okay. So KL divergence is a special case of f divergence with taking fx is x log x. Now if I do that, fx is x log x, then df for this is qx remains, and then in place of f I have so since I must substitute px by qx, so this is px by qx log px by qx dx, right? So the way I choose x log x, I made it cancel because in KL I need to add px, and it's px log px by qx, which is exactly the KL. Okay. So this is indeed expectation of log p by q. Which is the KL between p q. Okay. So f divergence is a more generic form, right? It's a more generic way to define a divergence where I can choose f to be a generic convex function with the restriction that f of 1 is 0. In this case, of course, f of 1 is 0, right? Because log 1 is 0. So f of 1 is 1, log 1 which is 0. So that's so from here you see that now you can generate infinitely many divergences. because you just put because convex functions are infinitely many, that will satisfy f1 equals to 0. Okay, so that gives you a very generic generalization. So as a research student, one of your starting point itself could be this, where you look into different f, take some convex functions with f1 is 0, and just see apart from the GANs which have been derived from KL divergence, you have opportunity to explore many other type of divergence. Maybe KL is good for image processing task. You look into some other applications where some other divergence measures will be the best. So we have now introduced F divergence. Now comes another key idea. Okay. So this is how you see how researchers build on things. Okay. Now there will be a guy called Nguyen. He found something interesting, but he himself did not figure out GAN. There was another guy who thought who built on the Nguyen's idea. So Nguyen, what he did is that he said that computing this integral is difficult, and such measures are needed in other statistical problems. Okay, let us not say GAN or something, but I just want to compare two distributions, and this itself is an important problem to study. But the problem is sometimes like doing this integration is not easy, and that's where the variational approach comes. Integration is not easy, but can I use some test functions for which it becomes tractable? Okay, so that's where the Nguyen idea will come. Okay, so now I use the word lower semi-continuity. I will briefly describe. These things are discussed in detail in convex analysis course, another course that I teach. You can watch those videos on the YouTube. So I won't go in detail. Lower semi-continuity is a, I will just by passing, okay, I will define. So F is, sometimes it's called LSC, okay, lower semi-continuous, if and only if limit x tends to x0, fx is greater than equal to fx naught. Okay, so what this means is that functions like this are allowed, are called lower semi-continuous. So what this says is that it can be convex. Some kind of discontinuity is allowed, but those kind of discontinuity that are allowed are of the type of lower semi-continuity. Okay, not any generic discontinuity is allowed in your F, but you are allowed to have lower semi-continuity type of discontinuity, and the result will the divergence measure will be still okay. Okay, so this kind of discontinuity is allowed.
Is it in the upper neighborhood?
Now this is taking, okay, yeah, that's a good question. So this is like it is taking this value, and jump is on the right side. So x is going to x naught from the right, because I'm approaching x from the right. In the limit I can always go at x. Limit is defined until the discontinuity point as well. Okay, we say it's continuous when both limit match. In this case it's not matching for sure, where the right and left limit doesn't match. But if I'm going to x naught from the right, in the limiting I can go until very close. The limit does not say that at the point it has to be there, right? But so, and the limiting case x is approaching from here, then in the limiting case fx is larger than fx naught, very close to x naught, it's larger than x naught. So this is called lower semi-continuity. There is a definition of upper semi-continuity as well, but yeah, but in this case the more generic, I mean what it says is that you can have convexity and you can also allow lower semi-continuity, and then of course a continuous function is lower semi-continuous as well, but obviously the other way is not true. Lower semi-continuous is not necessarily continuous. We have seen it here. Okay, so equivalent statements for this are for LSC, and these are left as an exercise for you. These are like simple, I would say. Okay, if you have basic maturity, then you can do this. So fx less than equal to y. Oh, okay, I mean may not be for all because we use something called closeness. So y in R closed in x. So now you can say, okay, what about closed, right? So those who know a little bit about topology, they can. I won't go into that right now. Okay. So those who know what it means to have a closed set, then they can say that lower semi-continuity is the same as saying that this type of sets for any y, the set of x for which fx less than equal to this basically these are level curves. Okay. Then they must be a closed set. Or another way to say is that the AP graph. Okay. So these are only for those. You can take this as an exercise, but only for those who know a little bit about these things. Okay, topology, or like those who have done optimization class. Okay. So such that t greater than or equal to fx is closed in. Okay, so I leave this as an exercise, real analysis exercise. Okay, and so these are also your exercise, and then further exercise for practice for this is that the proof that the function fx is -1 if x less than 0, and this is 1 if x greater than or equal to 0, is not lower semi-continuous. Okay, so this is another exercise for you. You can prove that. Remember this basic definition, all of you know. Okay, these additional exercises you may not have to do. Okay, if you don't know topology, then it's fine. Okay, so we know that f is convex and some kind of discontinuity is also allowed for f, and then we have this generic f divergence concept. So additional exercises I have is write two functions that are both LSC and convex. Another one is, can we have a function that is concave but LSC? Prove or disprove. Okay, so these are exercises for you to kind of look at. Now, the next set of ideas that we have is can we have a tractable variant of f divergence? So what I said is the integral in the integrand in the f divergence is not easy to calculate in practice. So we will go to a step variational approach where we will make it tractable. Again, using key ideas from convex analysis. So tractable f divergence. So we want to compute dpq. Okay, that's exactly our goal, and difficult to compute in the current form. Difficult to compute in current form. Construct a lower bound of that. So that's our idea. Construct a lower bound. Lower bound that is tractable. Tractable or like doable in practice. Okay. So this is the set of steps that we want to follow now. So hence we go to a variational approach, which is, as I said, is a very generic way to think about integration problem when you cannot integrate in practice. So variational representation of f divergence. Now the key idea that we have to introduce to create the variations, so-called variations, is the idea of conjugate functions. Okay, so I will define the conjugate for you. Okay, again, those who do convex optimization problem, they know these things by now, but it's a simple thing, so it's not like you should feel bad about that. Or in more generic way is y transpose x minus fx. So it's like creating a new function f star from f. Okay, so that's called conjugate. So here f star is called conjugate function of f. Okay, and I can list one paper on this where you read a lot more about this convex function. But to explain this to you, what it does is that it goes from the point domain to the slope domain. So I can see a function sometimes as a points and sometimes as approximated by slopes. So if I have a convex, let us say convex for the moment, convex function like that, then what it says is that these are your pointwise values. But what if I see these functions as slopes like this? It's a collection of slopes, or in other words, it's a maxima of these slopes. Okay, so if I construct these tangents to the function and start taking the maxima of this, it will be this curve, right? So it's like this, right? So if I take maxima, then it picks this, then this, then this, then this, then this. You see, it's like an approximation of the original curve, right? So if I have the set of tangents for a function, if I take a maxima of this, it approximates the function. Okay, if I do it really well, it is the function. That's what it's saying. Okay, and you do it for each point, right? At each point I have a tangent, another point I have tangent. Obviously, it should be the maxima will be point-wise. It will pick exactly the points on the curve. Okay, so then that's the concept of this. So all this thing that you see here, it's like it is looking for the slopes, which is when multiplied to x is the function value. So there is a nice geometric intuition behind this. I will upload a paper on this because this will take some time for me. But all this means exactly what I said. So it is a maxima of a sequence of affine functions in x. Okay, so this is a affine function this is an affine function in t. Okay, so this is affine in t because it's of the form just t, right? And then these are like you can think of fx as like a constant. Okay, so if I'm looking this as a function of t, then this is kind of some affine function in t, right? So this is like affine in t, and I'm taking a supremum of a set of affine functions. So this is supremum of sup of set of affine functions. A generic result from convex analysis says that supremum of convex functions is convex. Okay, so recall supremum of convex functions is convex. Obviously, affine functions are convex. Okay, affine functions are convex. Hence, supremum of these affine functions is convex. Hence, f star is convex. Okay, so this implies, regardless of what f was, okay, f star t is convex in t, regardless of fx. Fx may not be convex, but f star is always convex as a function of t. Okay, so this is a very brief crash course on conjugate functions for you. If you want to know more, I go to my YouTube channel, Convex Optimization for Machine Learning, and there is bigger variant of this there. So this will allow us to create variations, but let us see how. Okay, so we have that f in the f divergence, right? So now the way we will create this variation is somehow introducing this as a f star, but but there I have f, right? So I cannot really put just the f star itself, right? Sometimes I want to know what is f in terms of f star also. Okay, so that's like, how can I write f in terms of x star? Here I have been given f, I created f star, but how can I substitute f with something in f star? That's what I am looking for, right? So okay. So for these, a very quick thing is, given fx is ax plus b, find f star. Okay, these are exercises for you. And negative entropy, okay, you can try this. So given fx is x log x, in fact this is exactly what is needed for the KL divergence, right? So this is interesting. So in this case, f star will be e to the y minus 1. So these are the exercises that you may try to do. You have to solve that supremum problem basically. Okay. So I mean, just to maybe just one example, I will kind of like do it for you. Okay, because so let us say I want to compute f star for this guy. Okay, so f star of this, let us do it quickly, and this is supremum over x, right? And then tx minus fx. So so in this case we will have supremum over x of tx minus fx is x log x. The way to find this supremum is that you fix a t. Okay, you fix t first. Okay, so let us say some t is fixed. Now for that t, because this function, to define this function for any t, I have to say what is f of f star of t, right? So in that case, like, let us fix some t and then supremize over x. So I fix some t, and then now this function to have a valid value, this should remain some bounded. Okay, if I'm taking a supremum, this should give me some finite value. Then I will say, okay, for a given t I give you finite value, for another t I give you finite value. So one essential requirement is that for that t this must be bounded. Okay, bounded above. Okay, so to check that this is bounded above, we will find the maxima of this. Okay, so if we find a maxima of this, we have to differentiate this, right? So for a fixed t, right now it's not easy to say whether it will be unbounded for certain values of x. So that's why I will try to kind of use a calculus to see what could be the maximum value for a given t. Okay, so for a fixed t, find the sup. Okay, so then I will take a derivative of that with respect to x, obviously, because I am solving this optimal problem with x. So this is my t minus, and then this is like product rule. So first function differentiation of the second plus second into differentiation of the first. So this is my some function, let us say g of x. So this is g prime of x I have done, and this is t minus 1 minus log x is 0, right? So I solve for t. I mean, I am finding a maxima, right? So I will take a derivative and equate it to 0. That's what I did. And then I will find an x for which this maximum was achieved, right? So this implies log x is t minus 1. This implies x is e to the t minus 1, which is what you wanted. In place of t, you can change it to t here, let's say. We are using t in place of y. Then this is the place where for any given t, the x for which this will be maximized is e to the t minus 1. So then you kind of like put this x there, okay, and then from there you will For, let's see, for a given t we have maximized. To maximize we took the derivative and equated it to 0, and that gave me x. Now I am supposed to substitute the x. So let us see, there is one more step, right? So this is the x for which this is maximized. So now f star t must be t of, let us call this the optimal x star is, okay. So t of x star minus f of x star. So this is t, x star is e to the t minus 1 minus f of x star is e to the t minus 1 log of, so this is e to the t minus 1 log of e to the t minus 1. So this is t e to the t minus 1 minus log and e gets cancelled. So this is t minus 1 e to the t minus 1. So t e minus 1 goes away, minus minus becomes plus. So now you can say this is your f star, which is e to the t minus 1. Yes, that's right, yeah. So the first question answer is negative v. So yeah, I mean I put a question mark for others to verify. So this is how you compute that, okay, and basically that's the idea, for which for a fixed t you just go ahead and see what could be the maximum value, and that gives you the conjugate, okay. So if you kind of plot this x log x by some software or something, I don't know exactly how this x log x looks like. At 1 it must be 0, at 0 it's undefined basically. So I don't really know how it looks like, but it could be like this, maybe, I don't know. And what this is telling me is that this is approximated by these guys, these slopes that I have. So this is what conjugate means. Now there is a small result, it's called Fensel's inequality, which relates f and this, okay. Fensel's inequality, and that says that, so from here we have f star y is supremum of y transpose x minus fx, and this, since it is a supremum, it must be greater than or equal to y transpose x for any y and x. So this is y transpose x minus fx. So this implies f star y plus fx is always greater than or equal to y transpose x. So this is called Fensel's inequality, which is straightforward here. Another thing is, as I said, if I am looking into the KL divergence or the f divergence to be more precise, then I am looking to create variations in f, and then I have created a conjugate function, and conjugate relates f star to f, that's fine. But in the f divergence I have f to be replaced. I am not, so I want f in f star, okay. So f in terms of f star, okay. So let us see. So conjugate of conjugate is what we are looking for. So if f is closed, meaning the epigraph of f is closed, and f is convex, okay, convex function, then there is a result called f star is equal to f. Now proving this result is called Fensel's Moreau decomposition. I do this again in optimization, okay. So but this could be taken as a project, okay, because it's a long proof. So okay, I lost one star. So what this says is that f double star is f, okay. So if I take a conjugate of a conjugate, then I get back f, and this is true only when f is closed and convex, not in general, okay. If your original function was convex, then it is valid. For f divergence, anyway we are looking into convex functions. This seems to do the trick for us, that I will do one more conjugate, and from there I know how to write f in terms of f double star. So this proof can be found in Rockefeller book. He's the main guy who derived convex analysis a lot. 1970 book. Okay. So the variational approach comes from the conjugate. Okay, and this is the variational approach. So this is follows from the paper Nguyen and Jordan, Michael Jordan, not the he plays basketball, right? Michael Jordan, yeah, not that one. He's another famous Michael Jordan in machine learning. Okay, so what they introduced this idea. They said that go inside f divergence and change it via convex functions, and it will involve supremum. Bring the supremum out, and that gives you a variational approach. So this is what we are going to do this. So claim that we make is that df pq, which is the f divergence, is supremum of t expectation of tx minus f star tx. So it will be a little bit clear what these t operators are. So let us try to prove these results quickly. Okay, so using variational representation, so we can also write fx is supremum over t. So we are using that Fensel's-Murer theorem. Conjugate of the conjugate we can do, and we can also write fx as supremum of tx minus f star t. Okay, to get back fx, and this fx is where, so we have used the fact that f double star is f. Now we will substitute this. Okay, so we have df pq is integral of qx supremum over t px by qx minus f star t dx. So if you see in the f divergence, I have replaced f by this guy. Okay, because f can be now replaced by this. So that's what I have done. I have written replace f by the variational form. Okay, it is variational form because for variety of t's I am approximating the function values. That's the basic idea of variational form. You approximate it via some smaller functions. Okay, so now if you look into this, our interest would be to take this supremum out, and what are the consequences we will have if we take this supremum out, because the problem here is that this guy is pointwise defined here. For a given x, I supremized, then I get something in x, and then for another x, I supremized over t, and then I got another value. So this is given in a pointwise form. Okay, so to make things tractable, we somehow need to put the supremum out. But if I put the supremum out, what will happen to this pointwise evaluations that you are doing for t? Okay, for each x supremized over t, you get the t star, you put the t star, that's the current value, and then for the another value, and so on, right? So so we can do a smaller simplification here because q can go inside, because Qx does not have t. So it's okay to put Q also inside the supremum. So this is supremum of t, Tpx minus f star t Qx dx. Now this is again a proof in full proof in real analysis, but I will give you an idea behind what goes into taking the supremum out, okay, without giving a full proof of this. So what is happening here is, look into this. What is happening here is, did I work out this? Maybe yes. Okay, so what is happening here is that this function in x that you see here, this is determined pointwise. For each x, I find a t for which supremum is achieved, and that gives me the function value. So if I have to explain this to you, then I will do like this. Although this is a continuous value, I have shown this as a discrete, but that's not the point. It's like you take all this. At each x, I'm looking for the t for which this gets maximized. So for each x, I'm doing this supremum problem, right? So let us say I did that, and for x1, the t for which it was supremized was, let us say, t1. So then the function value that I get is t1 px minus f star t1 qx. Similarly, I do go here and I do the supremum, and I find some t2. So p star x minus f star t2 qx. So you see, at pointwise, I have these supremum values, and this is the function I construct. And I have to take an area under that. Okay, I have to do the integral, and this is the integral we are looking for. Okay, so inside the integral, we have this pointwise evaluations going on. So what would it take if I take a supremum out, right? Because there is a pointwise evaluations going on. So this real analysis result, what it says is that, let us say your ideal function is this, right? Like what I have done here. And this you obtained via pointwise supremum. If you do take it out, if you do take the supremum out, obviously the pointwise integrand inside won't make sense. So what it says is that, can you find some operators in T like this? Okay, so let us say this is the ideal T operator that I'm looking for, and these are some different variations of these T operators that I can have, okay, around the ideal one, let us say. So what this result says is that, can I change this to an operator form in the sense that I see these as Tx px minus f of f star of Tx and Qx. Because once I want to go out, then it's no longer pointwise, because the integral will be applied for some given function, right? I cannot say give you point, find the area, another point, because integration is not defined like that. But inside it's fine, because inside for all x, it's pointwise is defined, and then the whole function is seen and then integrated. So if you take supremum out, then there is a difficulty. So what we are saying now is that we can't give you now pointwise value. So can you do some kind of, can you find out some operators in T for which having this function is equivalent to like having this operator T x. So I mean Tx, which gives me, for a given x, it gives me the pointwise value T1. Okay, so can I have an operator which, given a pointwise value x2, it gives me T2 for here. Okay, so now it's more of an operator theory approximation things, right? So if I have to take the pointwise thing out, then, and I have to find a supremum among all of this, so that it eventually kind of, there will be one operator T star x for which the whole pointwise thing can be seen as one operator that actually gives me those optimal pointwise values. So this is the main trick here. One can rigorously prove this as a project, But what I am going to do now is that I will take the supremum out and replace these by operators. Okay. So this is supremum of, so this is what it takes to take the supremum out, and this is yeah, so this is integral of over x, and then I replace these pointwise values by tx minus f star tx, and then qx dx. Okay. Now this is what the variations we were looking for. Okay. Now this tx is kind of the test functions that I can employ and maybe make this integral tractable. Okay. So overall we can now write this as, so we are into this kind of min-max form, and where we can, so today's class is about theoretical derivation of the GAN, and this is when we end up into the min-max problem. Now how we will implement it, it will be the next class. Okay. So today I will kind of like go until the min-max. So tx to r, and this is expectation of, so I can write the first term as an expectation in tx of x from p, and minus expectation second term is coming from q, and this is expectation of f star of t of x. Okay, so this is the expectation taken over this guy. So this is a very strong approach, because if I take any fixed t, since it's a supremum, for any choice of t, it will be a lower bound. Okay, so any choice of t, any choice, once you instantiate the tx, so any choice of tx gives lower bound, and hopefully tractable. Okay, gives lower bound on this estimate, lower bound. So this is like just now the 3 lines I have to write. Okay, and then I will stop at min max. Okay, and so now using parametrized family of functions t phi to approximate the optimal function t. Okay, we are obviously looking for the optimal t, and then we can use some function approximator, right? Like let us say t phi, it could be some neural network. Okay, t can minimize an f divergence between p and the push forward p theta by solving. So then we will be solving this arg min, because we are parameterizing by this phi, because we are approximating this t phi, t by some t phi, and then we have theta in the p theta. So we have maximum likelihood estimates going on here, and I mean at least in theory, right? So then we can write this as, so let me write first. So this is because I have to do supremum over all the t. So and these t's are approximated via t phi. So that's parameterized by phi, and then we have expectation of x t phi x minus expectation of x p theta f star t phi x. Okay, so what I will say is that this could be a good place to stop as far as theory is concerned. It may look a little bit abstract to you, but trust me, this is what GANs will be. Okay, one of these guys will be discriminator, one of these guys will be generator. We will introduce neural networks. In fact, t phi x will be some neural network. F star will have a role here to play. and from here onwards, specific GAN architecture can be developed. So from theoretical point of view, you have a template to create variety of GANs essentially by just changing the T5. Okay, so that's one possibility, and changing the F also. Okay, that's so GAN was just one special case of this. So I would say this is a good place to stop as far as theory is concerned, and from practical point of view, we will specify exactly what it needs to be done for this min max and write a full algorithm of how to train and start generating with GAN. Okay, so let us stop for today.